So it says some students investigated the rate of decomposition of hydrogen peroxide. The equation for the reaction is hydrogen peroxide breaks down into water and oxygen. It says to complete the sentence, choose an answer from the box. So it says the student tested the gas produced to show that it was oxygen. The student used for oxygen, the test would be a glowing splint, and it would relight a glowing splint. There are three other tests that you need to know: the test for chlorine, the test for hydrogen, and the test for carbon dioxide. But the correct test for oxygen would be a glowing splint. Write that one in there. So nice, easy, 1 mark. Okay, it says student A investigated the effect of the particle size of manganese dioxide catalyst on the rate of a reaction. This is the method used. It says measure 25 centimetres hydrogen peroxide solution into a conical flask. Add some fine manganese dioxide powder to the conical flask. Measure the volume of oxygen produced every 30 seconds for 10 minutes. Repeat steps 1 to 2 2 more times. Repeat steps 1 to 4, but with coarse manganese dioxide lumps. It says, B, the method student A used did not give repeatable results. How could student A make sure the results were repeatable? Now, if you look at what student A did up here, he was very, very specific with the volume of hydrogen peroxide that they used. So they used 25 centimetres of hydrogen peroxide solution, but he wasn't very specific, or she wasn't very specific, with the mass of the manganese dioxide that they used. They've just used this word some, which means that some, it's not an exact amount. One time you could use more, the second time you could use less. So we need a way of controlling that variable, and that would give the student A repeatable results. So we need to see if there's anything in here that would suggest that. So it says tick one box. So we need to read that instruction properly so that we are only going to tick one box. So it says student A should make measurements every 2 minutes. That won't make a difference. Student A should measure the mass of manganese dioxide. That sounds like a good one to start. I'm going to put a little tick in there. Student A should use 50 centimetres cubed of hydrogen peroxide. Not going to make much of a difference. And student A should use a beaker instead of a conical flask. Again, not going to make much difference. So it is the mass of manganese dioxide that's essential, that we control that variable. It says student B used a method which gave repeatable results. How could student B improve the accuracy of these results? Okay, so it says calculate a mean, but do not include any anomalous results. That sounds like a good one to me, because we do like to calculate a mean to improve the accuracy of our results. Calculate a mean, but do not include the first set of results. Don't think that sounds like a good one. Record the results in a table and plot the results on a bar chart. Record the results in a table and plot the results on a line graph. I think this one sounds the most appropriate. To improve the accuracy, we're going to want to calculate a mean, but we don't want to include any results that don't quite fit the pattern where an error has occurred. So our anomalous results we want to leave out. Okay, the next part of the question says, the figure below shows student B's results for coarse manganese dioxide lumps. So we've got the volume of oxygen in centimetres cubed on the y-axis, and we've got time in seconds on the x-axis. Now it says calculate the mean rate of reaction between 30 seconds, so I'm going to just underline that, and 250 seconds for coarse manganese dioxide lumps. And it's been very kind, it's given us the equation for the mean rate of reaction. So it tells us we've got to calculate the volume of oxygen formed, and we've got to divide it by the time taken to form that amount of oxygen. It then says give your answer to 3 significant figures, so I'm going to underline that as well so that I remember to do that. Okay, So first of all, it says get the volume of oxygen formed between 30 and 250 seconds. So what I need to do is I need to look at my graph. And this big box here is worth 100 seconds. And there's 10 very small boxes in this big box. So that means that each individual tiny box is worth 10 seconds. So I'm going to count up to 30 seconds because that was the first time we had to find. So I'm going to go up to 30 seconds. So that's 10 seconds there, 20 seconds, 30 seconds. Now hopefully I can draw a straight line. Hopefully, obviously you would do it with a ruler. So it reaches there and we're going across and we've got 20 centimetres cubed. That's how much gas we had at 30 seconds. Then we need to go to 250 seconds. So we're going to go from here. So we've got 210, 220, 230, 240, 250. Exactly right in the middle between 200 and 300. I'm going to attempt to draw another straight line. Again, you guys will have your ruler. I'm not as fortunate on the little iPad I've got, but we'll attempt to do a straight line. Okay, so straight up to the top there, and I'm going to go across and see how much gas I had made in that time by 250 seconds. Okay, oopsie daisy, there we go. Right, so again, one of these small boxes here is worth 10 centimetres cubed of oxygen, and in that box there are 1, 2, 3, 4, 5 small boxes. So that means that each small box is worth 2 centimetres cubed of oxygen. So we've got 52, 54, 56, we've got 58 centimetres cubed of oxygen. Okay, so the difference in the gas collected between 30 and 250 seconds is we ended up with 58 centimetres cubed, sorry I forgot my little cubed, of oxygen gas at 250 seconds, and we started with 20 centimetres cubed of gas at 30 seconds. So we need to work out that difference. So our volume of oxygen would be, is 58 minus 20, which gives us 38 centimetres cubed. Okay, and the difference in the time taken is 250 seconds, because that's what it says in the question, minus 30 seconds. Okay, right. So that gives us 220 seconds. So I've got my volume of oxygen produced in that time, and I've got the time it's taken to produce that volume of oxygen. So all I need to do now is I need to put it into this equation that they give us here to calculate the mean rate of reaction. So the volume of oxygen formed divided by the time taken. So that's what I'm going to do down here. So it's 38 divided by 220. Now I'm going to put that into my calculator because I can't work that out in my head. So let me just give me 1 second. So it's 38 divided by 220 equals 0.1727, and that would be centimetres cubed per second. Now if we go back up a little bit, it says here you must give your answer to 3 significant figures. So I would lose a mark if I didn't put this into 3 significant figures. So I'm going to put my answer in here to 3 significant figures. So to 3 significant figures, I would have 0.173 centimetres cubed per second, because obviously my 3 figures are here, 0.172, but my next number is a 7. So because it's above 5, it's 5 or above, I'm going to have to round up. So it gives me 0.173 centimetres cubed per second. And the units are already given to us in this question. It then says E. Fine manganese dioxide powder produces a higher rate of reaction than coarse manganese dioxide lumps. Sketch on the figure above the results you would expect for students B experiment with fine manganese powder. So what we're going to assume is obviously that the volume of the hydrogen peroxide is the same, and the mass of the magnesium dioxide is the same too. So what I'm going to do is I'm just going to erase this off here, just so that we can see it a little bit better. Now, what it's asked me to do basically is to sketch on the graph. This that's already here is a graph for coarse manganese dioxide lumps, and it wants me to sketch a graph for fine manganese dioxide lumps. So what it's basically asking is, do you know what an increase in surface area by making the manganese dioxide fine lumps, what that would do to the rate of reaction? And if we increase the rate of reaction, we are going to get if we increase the surface area, then we're going to get a faster rate of reaction. But because we've got the same mass and because we've got the same volume of hydrogen peroxide, we're going to end up at the same end point. We're going to end up producing the same amount of oxygen in total. We're just going to get there faster. So I'm going to sketch on here. We need to start at the origin, because if we don't add anything at all, like if we don't have any manganese lumps, before we start adding them, etc., we don't get any volume, okay? So we're going to start at the origin. We're going to go up a little bit of a faster rate of reaction. But we are, hopefully, if this allows me to, going to stop at the same point. Okay. And then the question says, does it say we have to label it at all? No, it doesn't. It doesn't say we have to label it at all. Okay. So just sketch on the figure above the results you would expect for student B's experiment with fine manganese dioxide powder. So just to confirm, because it's a fine manganese dioxide powder, we will get a mark for starting at the origin. Okay. We will get a mark for making sure, or a correct answer would be to make sure that the rate of reaction is faster, so it's a steeper curve, and that it finishes at the same point, because we've not increased the volume of, or the concentration of the hydrogen peroxide, and we've got the same amount, mass of manganese dioxide lumps. Question F says hydrogen peroxide molecules collide with manganese dioxide particles during the reaction. Why does fine manganese dioxide powder produce a higher rate of reaction than coarse manganese dioxide lumps? And it says fine manganese dioxide powder has a larger surface area, fine manganese dioxide powder has larger particles, or fine manganese dioxide powder produces less frequent collisions. The only one that makes sense there is the top one. So if we have fine manganese dioxide powder, we would get an increase in the surface area, which would increase the frequency of collisions, increasing the rate of a reaction.